So without further ado, I'll turn you over to Brian. He'll talk about one of his many, many passions, the history of computing and the Manchester Mark I prototype. Take it away, Dr. Shelburne.
Thank you. I've always been fascinated by history. In fact, I read a lot of history, and I've been fascinated by computers. And so the history of computers is kind of a natural thing for me. So I want to talk about something called the Manchester Mark I prototype. It's actually the first computer to run a stored program. And I want to talk a little bit about it. I want to sort of set the historical context for all of this stuff. To begin with, I guess 2016 was the 7th anniversary of the ENIAC, which was the first all-electronic computer. It went online in 1946. But the ENIAC was not a stored program computer. That distinction probably goes to the Manchester University's Mark I. This is Manchester University in the United Kingdom. It was a prototype. It's also called a Small-Scale Experimental Machine, or SSEM. And it successfully ran the first stored program, which is called Kilburns' highest factor routine, on June 21st, 1948. So 70 years ago this coming June. We'll look at the code for the Kilburns program and show you how the Manchester Mark I prototype, it only had 32 words of 32-bit memory with 7 instructions. There was no division instruction in there. It was used to factor integers. We'll look at some other early programs which ran on the SSEM, including one written by Alan Turing, the famous computer scientist who at that time moved to Manchester. Basically there are no surprises here, but it's interesting to see how so much could be done with so little. So kind of an overview, I want to talk a little bit about computers in the late 1940s when all this began. In particular, I want to talk about the problem with computer memory. A lot of this was basically working in technology to address this problem. And it was the first example of what we call random access memory. Random access in that you could basically access any word in memory independently of where the word was in memory, unlike sequential memory. We'll look at the small-scale experimental machine, which is actually designed to test the Williams tube memory. But they made it into a full-fledged computer, and they actually ran some programs on it. I want to show you how you program the SSEM. I'm going to be careful here because a lot of it's kind of tricky, but I want to show you some of the tricks they did. And then sort of at the end, what came of this. So a little background with the early computers. There were 5, these are actually programmable calculators. This all happened around the time of World War II. It's kind of interesting how in various parts of the country, of the world literally, people were actually tackling the problem of trying to build some sort of electronic or some sort of computing device. The Nakata computer was built at Iowa State. It was a special purpose computer to solve systems of equations. In Germany, Konrad Zuse was a German aircraft engineer, and he built his computers, of all places, in the living room of his parents' apartment in Berlin. Fortunately, nothing really came of this. At Harvard University, there was the automatic sequence controlled calculator, which was Howard Aiken's baby. It was built with IBM money. And there's a very, very famous story about during the dedication of this electromechanical computer, which he kind of snubbed T.J. Watson, who was the head of IBM at the time. Watson got upset and went out and built his own version of the computer here. But these two computers, there's an example of the Nakata computer. It's a rebuild. And there is a picture of Konrad Zuse's Z4. It's a replica. And that was the Harvard Mark I. But the real interesting computers, which bear on the Manchester Mark I, is the ENIAC, which was built in the United States, and it was all electronic. It was not a stored program computer because you had to program it by basically rewiring the computer. And the Colossus, which was basically unknown until the 1970s, this was an electronic computer which was designed to decrypt German war codes during World War II. Unfortunately, they were all destroyed after the war. It was a big hush-hush secret, nobody talked about it. And in the 1970s, people sort of began looking at this. But why this is important, why both of these examples are important, is because this was the first large-scale use of electronics to build computing devices. The other thing which is not mentioned here was a lot of radar technology went into this. So during World War II, there was a lot of interest in building electronic circuits and radar, and this was basically the technical background for later computer development. So let's get into what a stored program computer is. It has both code and data stored in a single memory. And the code is stored as numeric values which can be modified by arithmetic operations. So instead of having a separate mechanism for your code and separate data storage for your data, it was a unified memory. So there's a picture of the ENIAC. And there's, interestingly enough, that this picture somehow, this is shot in 1944, like I said, after the war, the Brits had destroyed all of the computers and made the whole thing hush-hush. I'm not quite sure how this picture survived the end of the war. So let me talk about the problem with memory. And at this time, there were only three types of memory. There was obviously vacuum tube-based circuits. There was something called an acoustic delay line, which was actually old radar technology. And then you had magnetic drum storage. Well, here's the problem with vacuum tube flip-flop circuits. It's huge. This is just one decade unit from the ENIAC, and over 200 of these were needed. So they used a lot of power, used a lot of vacuum tubes. It was not the way to go. This is a dead-end technology from the start. The second one was called the Mercury delay line tube, and actually this was from radar technology. The idea was that you actually stored the bits in a column or in a tube of mercury as sound waves. And they kind of propagated through the tube, and at the end they were whipped around at lightning speeds, and they were fixed up and sent to the other side. So basically you're circulating this information through this tube of mercury. And a lot of the early computers used mercury delay lines. There were some drawbacks to it because they were very, very finicky. You had to keep the mercury at a particular temperature and stuff like this. So, that's an example of mercury delay line tube. All the electronics is on the outside of it, and inside you have this tube of mercury. They were very, very finicky to work with. And this was not random access memory because you had to wait for the bits to come around that you wanted to get. So you had to wait. It was sequential memory. The other kind of sequential memory was magnetic drum storage, where basically you had a magnetic drum and you had all these read-write heads. The drum spun very, very quickly, and you could read information and write information onto the spinning drum. Again, it wasn't random access because you had to wait for the drum to come around to the information that you wanted to get. So this is all we had at the time. And so this is what happened with Tom Kilburn on the left and F.C. Williams on the right. They were both engineers who during the Second World War worked at the Telecommunications Research Establishment in the UK, which developed a lot of radar. And it was basically Williams on the right, who got the idea of perhaps creating a type of electrostatic storage using a cathode ray tube. Okay? So essentially, Williams is appointed professor of electrotechnics at the University of Manchester in late 1946. This is after the war, where he was joined by Kilburn, who was actually one of his students, with the intention of researching a computer storage system based on cathode ray tubes. Okay? And they jointly patented the CRT technology, which bears Williams' name. And in 1947, they were joined by Gottfried Teutel, who actually you'll see later on, also from the telecommunications research establishment. These are all basically radar technicians. These are radar engineers. They're using a lot of radar technology, okay? And in 9 months, they built the small-scale experimental machine as a minimal computer testbed around CRT storage. And as I mentioned, during the war, they were involved with radar. So this was actually a patent for the Williams tube. And the idea is that you can store bits on the face of a CRT tube, and you can read them and write them. And one of the side effects, which was useful, is that you could actually look at the tube and you could read off information from it. You could tell a 0 from a 1. And so they exploited this in building the small-scale experimental machine. They developed this technology. It was truly random because you could aim the electron gun any place on the screen and immediately pull off all the bits at that place. It's basically using a television tube to store your information. That's kind of what it looked like. It was kind of a small tube in front. I think it was about 6 inches across. And by the time that they had a small-scale experimental machine up and running, they were able to store 1,024 bits on one of these tubes. So basically you had 32 words of 32 bits. If I can sort of go back to this picture, what you see is Kilburn and Williams in front of the SSDM, and that round thing in front of you, that is a Williams tube. Okay. And as a matter of fact, this is actually the, you could actually program this thing by using buttons. This sort of an example of that. Okay, and actually I said one of the side effects of this is that you actually displayed on the tube your memory. So what you see here is where the dashes are, those are 1s. And where the dots are, those are 0s. It's kind of like Morse code, okay? And if you count very, very carefully, you will notice that there are actually 32, there's 32 columns and 32 rows. And you scan across like that. So that's how they read off memory. They looked at it like this. Okay. So this is a picture of the Manchester University Mark I baby. Actually, it's not. As soon as they got the thing working, they went on to develop the Mark I, the full Mark I, and they scavenged a lot of the parts from the old SSEM to do this. I think this came about 1949. But what you see are sort of parts of the old SSEM which were used again to create the real Mark I computer. So what I want to talk a little bit about is some of the details of the SSEM and how it was programmed. Okay. So, hope I don't go too fast here. Memory was 32 words of 32 bits. You had an accumulator register. Basically, what that meant is that if you wanted to perform a calculation, you'd load one of the operands into the accumulator register, and then you will literally subtract a second operand from memory into it. You had a current instruction register, which is like a program counter, okay? And it contained the address of the current instruction, which is kind of interesting. Usually today computers contain the address of the next instruction. And you had a present instruction register. You actually had 3 of these tubes. One tube had the memory, a second tube just contained the accumulator, and the third tube contained the 2 lines for the current instruction and the present instruction. And as I mentioned, the current instruction, the CI register, held the address of the current, not next instruction. What was really strange about this was that all the numbers were displayed in reverse binary, which meant that the least significant bit was on the left, not on the right. So you had to read this thing off backwards. It makes it a lot of fun to try to read the screens and try to figure out what's going on. So they were displayed in reverse binary, with the leftmost bit being the least significant bit, okay, which is done just the opposite today. This is kind of a diagram of the SSEM. You see this accumulator, CRT on the left, the store in the middle, and the third CRT on the right. You had an adder and subtractor. It was really kind of a jury-rigged computer. I mean, it was minimal. The whole idea was just we want to test to see that this technology works for storage. And so there wasn't much that this computer, in theory, had. Okay. There were only 7 instructions. Okay, they had 3-bit opcodes. And the instructions are quite interesting. The first instruction was a jump instruction, and it was what we would call today an indirect jump instruction, because the idea is that the address contained the target. So if you said jump 28, you had to go to location 28 and get that value, and that was where you were going to jump to. So you had an indirect jump. Jump, JMPR, was a relative jump, which is kind of interesting too, because what you did is it said jump JMPR 28. You went to address 28, and you actually added that value into the current instruction. So it was a relative jump from the current location. Let me go on. The load was load negative. You didn't load the accumulator, you negated the loaded. So you load negated. There was a store instruction, so you basically wrote the contents of the accumulator out to storage. And the only arithmetic instruction was subtract. So you do a load n, and you subtract. So everything was kind of backwards. Okay. There was a skip instruction. If the accumulator was less than 0, then you would skip over the next instruction. And of course, you've got to have a halt instruction because you've got to stop the computer somehow. So that's all you had, 7 instructions. But it turned out you could do anything with 7 instructions. The only limitation was the amount of memory which you had, which is just 32 words. The other thing is, I mentioned the twos, use two's complement representation. Don't worry about what that means. But the values were stored in reverse order, reverse binary. I think I mentioned that 13 was stored with the 1011 on the left, instead of today we'd see that with the 1101 on the right. And the sign bit was on the right. And bit 31 was a sign bit. So if bit 31 was a 0, it was a plus sign. If it was a 1, it was a minus sign. So you could tell plus and minus numbers. So this is all very, very useful if you want to read information off the CRT. The instruction format. Well, we had 32 bits, but we only used, 8 of them. So the first 5 bits was the line number, was basically the operand address. And bits 13 through 15 was the function. So you didn't use all these bits. They had not much instruction here. The other thing which is kind of interesting too is since the current instruction register held the address of the current instruction, hence the name, instead of using the fetch, execute, increment cycle, you always would increment first. What Turing did is he took this technique and programmed the SSEM to do this. It took him all 32 lines of code. He did a few tricks here. And I'm not going to spend much time on this because it's pretty gnarly programming. But he set up the divisor lined up already with the dividend. Okay, so he had to move the divisor over by a factor of 2. Okay, or a power of 2. And basically, again, in front of you, the initial dividend was in line 31, and the divisor shifted by a power of 2 was in line 30. And you shifted B enough so that you could subtract B from A and get a positive value out of this. You subtract the divisor from the dividend. It's either going to go in there or not. It's either yes or no. Okay, if negative, go to line 20, which is next page over. Otherwise, you make the dividend positive, the divisor's too big. You shift the quotient So, I will confess I felt a certain affinity. You know, I'm working with Turing. Okay, third one was Toodle's highest common factor program. It's all there. Again, basically it's just Euclid's greatest common divisor algorithm, which we always have students do in the introductory programming courses. Just basically uses repeated subtraction to find the remainder. It's not much different from Kilburns, a highest common factor routine, okay? Except that it keeps going. So what was really interesting was in 1994, they realized that the 50th anniversary of the SSEM was coming up, and they decided to do a rebuild. That is, to rebuild the computer as much as possible. And the rebuild is currently at the University of Manchester. There's a picture of it on the right. That is what the baby looked like. There are lots of simulators out here that you can play around with. And you see, okay, the simulator's in two pieces, as a matter of fact. You have the CRT tube there, and you have the switches. I want to do this because this is essentially how it was programmed. You might notice that there are actually, if I can count them, there are actually 40 buttons up there. We only use the first 32. And what you would do would be you'd use these switches, okay, so I can get this right now. You use the upper 5 switches, excuse me, upper 5 switches to set that will give you the line number. Okay, so 0 through 31. And then you'd press the proper buttons up there to actually set the corresponding bit to 1. Okay. So, so the way you program it is that you basically, all the switches are off, you put in line 0, then line 1, line 2, line 3, line 4. That was the input. That's how you get the program in there. Okay. And then you hit the run button somewhere here. Okay. And it came up looking like that. Okay. So the baby was transformed to the Manchester Mark I. It was expanded to have a 40-bit word and included B lines, which were index registers, which was something new. It was actually marketed by Ferranti in the UK. The first one came out in 1951. There's some thought that this might have been actually the first commercial computer to come out. The Williams tube machines were used in a lot of early computers. The IAS computer, which was the Institute of Advanced Studies, which was also one of the prototypes for a lot of computers which were built in the early 1950s. Used the Williams tube. So did the IBM 701 and 702. Unfortunately, actually CRT tubes weren't that great. They were very finicky. But a new technology came along, which was ferrite rings, which is called core memory. We have some examples out in the display case of core memory machines. And that was your main form of memory until the late 1970s, early 80s, when IC memory, or integrated chip memory, came out, which we use today with SRAM and DRAM type memory. We've really fixed the memory problem. I mean, memory now is dirt cheap. And consequently, programming computers has gotten a little sloppy. We don't care how much memory you need, because we got plenty of it. But back in the day, when memory was expensive and wasn't very much of it, you had to be very, very clever to write programs that did anything. Oh, and thank you.